Problem 526. For this, we want to find the vector potential created by an infinitely long wire that carries a constant current. Now, we could try to do this using the Coulomb gauge. Remember, the Coulomb gauge is this. However, we have a bit of a problem. You see, for an infinitely long wire, this r prime goes out from negative infinity all the way over to positive infinity. And this r vector, that just represents a single fixed point. Now, infinity is really, really big, which means that no matter what r is, r prime is going to spend most of its integration region much, much bigger, which means for the most part, this integral is some value times 1 over r. Now, the integral of 1 over r is the natural logarithm of r, and the natural logarithm of r from r is negative infinity to positive infinity is not well behaved. You can't calculate that. So we're going to have to do something else. Now, to do this, we are going to rely on the definition of vector potential. The curl of vector potential is B. We also know from either the Biot-Savart law or Ampere's law that the magnetic field around an infinitely long wire is given by this formula right here. U sub naught over 2 pi times I divided by S, where S is the coordinate that they asked us to use. And it's always in the phi hat direction. So looking at the inside of our front cover, and because we're dealing with an infinite wire and phi hat direction, we're going to be using cylindrical coordinates. That just makes the most sense. If I arbitrarily said A was just some vector field, then the curl of A can be seen in the formula in your front cover. Now the curl of A is itself a vector, so it will have an S hat component, a phi hat component, and a z hat component. We want the curl of A to equal B, so we want the S component and the z component of this curl to be 0. And we want the phi component to equal this right here. So this is the S component, the phi component, the z component of curl. Now, I am going to make a guess. And that guess is, because the Coulomb potential always suggests that the vector potential goes in the same direction as J, and because J goes in the z direction, I'm going to guess that the vector potential goes in the z direction. So A will have a z component. That potentially could affect that term and that term. If A does not have an S component or a phi component, this goes to 0 automatically and we're done. Furthermore, since we're looking for something that depends on S here, if the z component of A depends exclusively on S, this term will go away. Now, some things to watch out for when using this method. If there was a phi term, it wouldn't matter what that phi term was. This would not necessarily go away because it's S times the phi term, unless the phi term was varied with 1 over S. So let's go ahead and stick with our guess. A is equal to some function az that depends solely on S. So I'm going to say that the derivative of that is equal to some constant value times 1 over S, which means what do you take the derivative of and it becomes 1 over S? Well, logarithm of S. So I'm going to say that A goes as the logarithm of S, but you can't take the logarithm of S because S is a dimensional value. So I'm going to say it's logarithm of S divided by S naught. What is S naught? It doesn't actually matter. It is just some point where I set the potential equal to 0. And the values that I need to put in, the constants that I need, is AZ is equal to negative mu naught over 2 pi I. All of this is constant, so it won't affect any of the other derivatives. And if you take the derivative with respect to S, it becomes 1 over s times this, and there's a negative there, so that cancels with that negative there, and it works. Now, this guess, it turns out, was not the only guess I could have done. I could have guessed, well, what if this comes from this term right here? For this, I would need an AS component that depends on Z. Now, AS component that depends on Z, that still doesn't cause any problems for here, because if it does not depend on phi, that stays 0. It's not an A phi term, so we don't have to worry about that. And there would be no AZ or A phi term, so we don't have to worry about that one. And it turns out we can get an answer that works for that too. We get A is equal to mu sub naught I Z over 2 pi s. When we take the derivative with respect to Z, the Z goes away, and so we're left with mu sub naught I over 2 pi s. The existence of two different solutions implies that there's actually a whole host of solutions that could work. Generally, if you did look this up against the expressed desires of the textbook, you would generally see it written in this form. And that's because even though we can't use the Coulomb gauge, we prefer to follow the conventions of the Coulomb gauge. And also, if we were going to do part B of this problem, look at the vector potential inside the wire, the only way we could get the vector potential to not be discontinuous at the surface of the wire would be to use this form.